Hi, welcome back. We are into lesson number 2. This is going to be our basic introduction to vectors, and in this we will talk about some different terminologies that are associated with vectors. We'll give you a sense of what a scalar is, what a vector is, the properties of a vector, and then we'll get into kind of some basic identities and how we can start to use those to work for us. So without further ado, let's get started. So as we start to kind of work our way into using vectors, we first need to understand exactly what they are and some of the terminology that needs to be applied to that. So the first term that you're going to encounter a lot in engineering is something known as a scalar, okay, which is a quantity which has a magnitude or basically a numerical size only. Some examples of scalar numbers are, the natural number is 1, 2, 3.7, and things like that. Speed, distance, energy, charge, volume, temperature are all scalar quantities. There's no direction that's associated with them. Now, one of the things that happens is that vectors are composed of objects that have both magnitude and direction. So it has a scalar portion associated with it, but it's also got another piece of it that tells me the direction. And in our last video, we talked about the different directions of that weight vector depending on where you were standing on planet Earth. That the weight itself, which is a magnitude, the vector direction was what was different. Okay, and so one of the things that vectors will let us do is we'll be able to start kind of putting some pieces together and being able to look at it. Now, from a mathematical sense, scalars are, if your classical rules apply, that if I have two values, a mass of 10 and a mass of 5, the total mass is 15. Those simple rules apply. Vectors are a little bit different, in which we have to now start associating with directions in x direction, y direction, z direction if we go with the Cartesian vectors. And so there's some special rules that we'll have to kind of talk about. Now, in the Beer and Johnson textbook for this class, okay, and in most common textbooks, vectors are generally denoted one of two ways. Now, they're either indicated as a bolded value, or as some letter indicating the vector A and then a hat over the top. Now, because my handwriting isn't the best, I tend to write this one because I can see the hat, whereas I can't see the bold. Okay, and the reason that we write it that way is that the magnitude of a vector is a scalar value and is typically written as some sort of magnitude operator with like absolute value signs wrapped around an A. I would argue that in most of the stuff we're going to start off with, I'm going to go ahead and be redundant and say put the hat on him. Okay, but the thing I don't like about the textbook that we use is they write it just as A. It's generally some sort of italicized, non-bolded thing. Well, without writing this extra information, I can't tell the difference between this or this guy, the bolded one. Okay, on a typeset you can kind of determine that, and it's pretty clear to see, but in handwriting it's very, very difficult. Okay, and I definitely can't make an italicized letter look like an italicized letter. Okay, it just doesn't work very well. So I'll be using probably these latter two to be able to kind of explain what it is that we're trying to do. Okay. Now, things to know when you're sketching a vector, and I'll have some more graphics here that we'll talk about, is that the reference direction is always indicated, the scale is indicated. Vectors are represented as arrows with a length that is proportional to their magnitude and are correctly oriented with respect to the reference direction. Okay, and I'll explain what that means here in a little bit. One of the things that's cool about vectors, if you draw everything to scale and at its appropriate orientation, you can actually solve some of these problems graphically. Okay, you could go into a drafting program like AutoCAD or MicroStation or something and actually lay these vectors in and then be able to figure out what the net resultant is. It's kind of a cool trick that you can do with these vector things. Now, I'm not saying that we're going to do anything that method, but it will form kind of the basis of what it is that we're trying to do. Everything we're going to do will be mathematics based, but it is possible for very complex problems to actually graphically recreate solutions to some of these problems. Okay, the direction of the vector is indicated by an arrowhead. Okay, and then the arrows should usually be labeled to show which vectors they represent. So if this is vector A, normally I put a vector A on it. In this class, we're doing lots of vectors of F or P, is a common one for force that we'll be dealing with. All right, so a couple of examples that you can kind of look at is, and you can see the source of where this came from many, many years ago, okay, is that we're given the statement that we walk 4 meters in a northerly direction and then 3 meters in an easterly direction, okay? And so if we set up our scale and we draw this thing, what that's saying is that starting at my start point, or my beginning point down here, I'm going to go 4 meters north, okay, that's what this is telling me, my direction, my orientation, and then I'm going to go 3 meters east, which will get me over to here, okay? So the net resultant of that path between where you began and where you ended over here is that guy, okay? And this is what we're going to be known as a resultant, and we'll show you different methods for being able to calculate those. Now, in this simple problem where we have, directions of north, east, south, and west, you know that that's 90 degrees. This becomes a right triangle, and I can actually find out that, oh, well, I moved 5 meters from here to here. Okay, now just saying I went 5 meters doesn't tell me anything. I also have to include the direction of this vector, which is the theta. Okay, and so that's the way that we would start to kind of look at that. So this is a very common triangle, 3, 4, 5 on a right triangle. Okay, and so the solution method then would say, well, if I know those pieces of our vector, then I can solve for this d dimension, which is the distance from my beginning to my start, as just simply being Pythagorean's theorem of 3 squared plus 4 squared square root, or 5 meters. That's where the 5 came from. Okay, and so that's how you would find the magnitude of the vector. And so that's one of the tricks that we can start to kind of look at. All right, so on to the next page. All right, so kind of adding to that, we're going to write this thing a little bit. Let's see if I can get the camera to focus a little better. Okay, and so basically vectors are quantities that have magnitude and direction. Okay, and in fact, I'm going to split this up, this direction term, because that's what we learned back in our high school classes, that direction that it has, it's just direction. But in reality, it's got not only a direction, but it's also got something about a sense. Is it acting to the left or is it acting to the right? And I'll explain that here in just a second. But basically the wording that you saw on the last page of this says that I'm going to draw a vector arrow as an arrow with a tail point or a start point here, indicated by the dot, okay, and then the head, which is the finish point, being up here at the end, okay? The length of the arrow is known as the magnitude, and again, whenever you draw these, if you're being pure to vectors, you're supposed to draw this to scale. Okay, now in this class, we won't do it so much. We'll rely on the math to tell us how long the vectors are. But if I wanted to draw things to scale, I could do so. Okay, what's more important is then the direction of this arrowhead. Okay, and so we'll kind of look at this. Now I'm going to break this down, and we're going to talk about something called a line of action. Okay, and that would be the first component of my direction, and then 2 is my sense. Okay, and the reason I break this down a little bit further is that because the line of action I generally know. I know that it's acting along a line, but if I have a very complex system happening on this and I've done my math, sometimes I don't know the sense. And what the sense is, and an example of that would be this case. These are the two vectors. They have the same line of action, assuming that they're acting on, at the same angle, but I have a force that is acting up the line, up and to the right, which would be one direction, and then the opposite vector is acting down and to the left. Okay, if this is my A vector, then this guy is denoted as a negative A. Everything else is the same. The magnitude is the same, the line of action is the same, it's just the sense is determined by the minus sign. Okay, and now what's cool about this is that by splitting it up and talking about splitting the line of action and the sense, you know the line of action. All right, so I can write an equation, and what will happen is if I write everything in a vector form, and all I'm worried about then is the magnitudes. When I go and I solve my equilibrium equation, we'll talk more about that, about what that means in the coming videos, that if there's an unknown value, say it's a support reaction or an effect on an object on there, that it's the resultant of a whole bunch of extra forces happening on this thing, that if I get the line of action right and I solve for the magnitude, the sense will be determined by the sign that's on that magnitude value. Meaning that if I do all this math and all of a sudden I come up with, a magnitude of -3, but I've assumed the vector was to the right, the negative sign tells me, well, in reality, it's a 3 magnitude vector that was actually acting to the left. It will self-correct itself. And that's really, really powerful. Okay, and so I don't have to be worried about, well, is my arrow in the right direction when I go write all my equations? It doesn't matter. As long as it's on the right line of action, the sense will self-correct. Okay, and so that's why I kind of split this out a little bit differently. You need both of these pieces to make up for the definition of direction as we learned it in the past. Okay, we talked a little bit about some of the denotation. Again, A and A hat, that's how I write as a vector. Okay, and then the magnitude will be some sort of arrow and then A magnitude. Now later on, eventually we'll start dropping this and we'll get it as we get more comfortable with what's going on, and I may just start writing this as A, okay, but I'll always write a vector with a hat on it. Okay, and that way I can tell the difference between this and this. If I see it without a hat, I know it's a magnitude. If I see it with a hat, I know it's got a vector and it's got sense and direction associated with it. Okay, all right. Now, some of the vector operations that we have, okay, we talked about the opposite sign. So this is an A vector, this is a -A. Okay, we can also get into adding multiple vectors together. So suppose I have two vectors, A and B. Okay. Okay, and we talked about the graphical method that can be used to construct these. Well, what's cool about this is that I can add these together such that A plus B is equal to R. Okay, so I've got an A vector plus a B vector is equal to some R vector. Well, if we go back to that picture that we had in the last example that we had here, I could say, well, it's an A vector from here to here, okay, and it's a B vector from here to here. He has a magnitude in a direction telling me north, and he has a magnitude in a direction telling me east. Then the R vector is the guy that goes from here, that goes from the beginning and ends at the end. Okay, this is known as the resultant of this particular system. Now the magnitude of that resultant we said was 5 meters. Now we just need something that tells me the direction that he went over there. And the direction that he went was 4 meters north and 3 meters east. Okay, and we'll show you some ways to represent all of that. Okay, and we'll get into things called unit vectors in the coming videos as we start to kind of look at it. So it's very, very powerful stuff. It's very, very simple. But what's cool about it is that now I have an equation for being able to find resultants. Well, this resultant in a physics sense, for an object is basically a mass times acceleration. Okay, this is Newton's second law happening here. Okay, or if you're studying statics, I can say A plus B equal to 0, and I can find out what's going on with A and B that causes equilibrium to be required. Okay, so this resultant has special terms. So the resultant is basically what happens when you add two vectors together. Okay, now if I look and I have a vector A happening here and another vector B happening down here, okay, that we can find the resultant, that the resultant actually connects. If I put A and B together starting at the same point, that the resultant is actually occurring somewhere between A and B, and it connects what would be the end point and the start point. Now, this actually is what we call a parallelogram. Okay, it's a four-sided object that has certain properties, and in the next video we'll talk about how I can use this to actually find out this R value in its magnitudes and its directions. But what's interesting is that if this is my start point and this is my end point, because that's what we define the resultant as, there are multiple paths I can take to get there. I could do A first and then come down B, where this line is parallel to this line, and it's the same length, the same direction. Okay, so for my B, as going then B and then A. Okay, so it's commutative. I can, A plus B is equal to B plus A, which is good from a mathematic. If you're a pure mathematician, we like that property, that the order of adding these things, the order of doing things does not affect the outcome of the numbers. Now, in some mathematical things, that's not always the case, but in our world, it is, and we like that. Okay, and so the parallelogram law, as we start to kind of look at this, is where we'll kind of go next. That vectors A and B are joined at the tail. Okay, that we're going to draw parallel lines from the head of the vector through each of the vectors through the common point. So I'm going to draw a line here, and I'm going to draw one here. Okay, and then I'm going to draw parallel lines through the head and the tail. So through the tail of A, I've got this line, and then I would draw another one here. And then for B, I would have the line through the tail and then the line through the head. That creates a parallelogram. okay, based on these parallel lines, okay? The resultant R is the diagonal from the tail point to the head point, as we start to kind of look at that. All right, now in the next video, we'll do some more with, actually computing resultants and playing with some of those games. But for now, we'll kind of talk about some of the different construction techniques that we have to be able to do things. So for now, we'll go ahead and stop. We'll talk about some different rules like the triangle rule and the parallelogram law, and then we'll get into some components and doing things a little bit less graphical as we had intended. So I know a couple short videos to get us started, but this is a big step, and I encourage you as you're studying vectors not to discount this method. Okay, I remember when I was an undergraduate on there, I knew mechanically how to do vectors, but I didn't realize until much later the power of what they can do for me. All right, so pay attention to this, and this will save you in a dynamics class. It will save you in a physics class. Magnetic field direction, current flow, all of that stuff. It can all be represented as vectors as you're starting to kind of look. And so I can't emphasize that enough. Don't gloss over this. Oh, it's just we start thinking vectors and math, and our eyes start to gloss over and roll over. Don't. Just put it to use and get some practice. And we will in this class. We'll practice these a lot in the first 4 chapters, and hopefully it will make some sense to what you can do with them. Very, very powerful tool, and it's a first step into a big world of engineering mechanics. So anyway, we'll go ahead and close this video out here now. As always, if you found it useful, please toss us a like or subscribe down below, and we will see you guys in the next video. Thanks. Have a great day. Bye.